All metals have some electrons free to move around. This means they're not attached to the atom itself. But all these free electrons are still held in the metal by electrostatic attraction from the positive charge of each of these nuclei here. But it is possible to eject these free electrons from the metal's surface. But this will only happen if we give these free electrons enough energy to overcome that attractive force from the nuclei. One way we can liberate these electrons is by shining some light onto the metal surface. But not all types of light will be able to liberate these surface electrons from the metal surface. This light needs to have a minimum frequency. Remember, the energy of a photon of light is equal to Planck's constant multiplied by the frequency of the light. So we need a minimum frequency, which we call the threshold frequency. And if the frequency of the incident radiation is high enough, is equal to this threshold frequency, then it's able to liberate these electrons here. But if the frequency of this light isn't high enough, so for example, instead of yellow light here, we have red light, which has a lower frequency, and this lower frequency is smaller than the threshold frequency, then electrons don't get ejected from this metal. And the thing is, it doesn't matter what the intensity of this light is, so how bright it is, or for how long you shine it onto this metal. If the frequency of this light isn't at the threshold frequency or above, then these free electrons will never be emitted from the metal's surface. Now, for this specific metal, the threshold frequency is equal to yellow light. So blue light has a higher frequency than yellow light. So blue light shone onto this metal will be able to also liberate these electrons. Now, when electrons get ejected from the metal's surface, this is called photoemission. And it's simply what we call the release of electrons from the surface of a metal when the electromagnetic radiation is incident on the surface. And these electrons are called photoelectrons. But different metals have a different value for this threshold frequency. So for example, platinum would have a different threshold frequency than zinc, for example. And this simply means that each of these metals requires a different frequency of light, a minimum frequency of light, to be able to eject electrons from the surface of that individual metal. And this comes down to how the individual metals hold on to their free electrons. Some metals will hold on to them more strongly than others. So we saw in the last lesson that electromagnetic radiation consists of photons, and it has a particle nature. So when a single photon hits the surface and strikes one of these free electrons, it will only react with that single electron. It can't transfer its energy over to multiple electrons. If we have a photon that has a frequency that is above this threshold frequency here, so for example this photon, because this photon's frequency is higher than the threshold frequency, if it strikes the surface and hits one of these free electrons here, then it will give the emitted electron extra kinetic energy. So in other words, if we get a very high frequency, or the higher the frequency, the more kinetic energy this photoelectron will have. And the more kinetic energy it has, the faster it will shoot off the surface. Because kinetic energy is equal to half times the mass of the electron times its velocity squared. Now each metal also has its own work function energy, and this is the minimum amount of energy necessary for an electron to escape the surface. And this work function energy has units of joules. If we have a photon at the threshold frequency, so this photon for example, and it hits the metal, the photon will just about have enough energy to liberate the electron from the surface. So this electron here will not have any kinetic energy. It will not fly off the surface at a certain velocity. This means that the energy of the photon with the threshold frequency is equal to the work function energy, which again is the minimum amount of energy to liberate this electron. And we can write this all out with the photoelectric equation. So if we have the energy of the incident photon here, so h is Planck's constant, f is the frequency of the incoming photon, that will be equal to the work function energy, which is the minimum amount of energy required to liberate an electron from the surface of the metal, plus the kinetic energy of the final photoelectron. And here we see the conservation of energy in effect. In other words, the total amount of energy coming in from the photon here is equal to the final amount of energy of this photoelectron here that's been emitted. This photoelectron will have some kinetic energy if the frequency is high enough, but this electron, this photoelectron here, also has to overcome the work function energy to escape from the metal. And in fact, we can replace this work function energy symbol here with the threshold frequency. So the energy of a photon with the threshold frequency. So we have a question here. The work function energy of platinum is 9.0 times 10 to the power of minus 19 joules. Calculate the threshold frequency for the emission of photoelectrons from platinum. So the work function energy is simply the minimum amount of energy required to eject an electron from the platinum surface here. And we know that to eject this electron, we need a photon with a threshold frequency for this platinum here. So this is the energy of the photon required to reach this work function energy here. And the question asks us to find this threshold frequency. And we've got Planck's constant down here. So the frequency, the threshold frequency, is equal to the work function energy divided by Planck's constant. That equals 9.0 times 10 to the minus 19 joules divided by 6.63 times 10 to the minus 34 joule seconds. And the joule units cancel out, leaving us with seconds to the minus 1, or 1 over seconds. And this comes to 1.4 times 10 to the 15 hertz. So part 2 is asking for the maximum kinetic energy of a photoelectron when radiation of frequency 2.0 times 10 to the 15 hertz is incident on a platinum surface. So we already know that this is the threshold frequency, so the minimum frequency to eject an electron, and this electron will have no kinetic energy. But now we're given another photon of light with a higher frequency So this extra energy is going to be transferred to the photoelectron as it leaves the surface. So we got the photon coming in, and it will eject the electron with some kinetic energy. Now our goal is to find the maximum kinetic energy, which simply means that these electrons would be closer to the surface. So free electrons that are further into the metal will require even more energy from the photon to escape, which will mean that their kinetic energies will be slightly lower. So the maximum kinetic energy is for electrons that are right on the surface. So if we go back to our photoelectric equation, the incoming photon, the energy of the incoming photon is equal to h threshold frequency plus the kinetic energy, or the maximum kinetic energy, of the ejected electron. Now all we need is the kinetic energy here, and we already have this energy here because it's the work function energy, and we're given this value here, which is the energy of the incoming photon. And we can work this out by multiplying the frequency here by the Planck's constant. So if we bring the work function energy over to this side of the equation, to the left hand side, we can isolate the kinetic energy. So the Planck's constant is 6.63 times 10 to the minus 34 joule seconds, and we multiply that by the difference in the frequencies between the incoming radiation photon and the threshold frequency that is required to just about get the electron off the surface. And we end up with an answer of 4.0 times 10 to the minus 19 joules. And if you wanted, you could go further and find out the velocity of this ejected electron.